Okay, please welcome our next guest, Cyryl Matuszewski from Qlog, and he will tell us about optimization between GPU and CPU.
Okay, hello everyone. My name is Cyryl Matuszewski. I work in Qlog and I'm a porting programmer, so it's some kind of engine programmer, basically having to do with ports. I work in this industry for about 9 years and I've been doing ports from different consoles, so I have quite a major experience in optimizing the games on PS2, 3, Xbox One, 2, 3 and so on up to the the current gens, and of course the PC, because this is the part where we are specializing the most. Now, when you look at the topic and you can see the word GPU, so for me it's usually okay, I will see some fancy pictures or some new algorithms for the GPU. Sorry, not this time. We are going to talk about the optimization. So the main part is the communication. I'm going to show you the optimization things that probably all of you do when doing the rendering, but from the communication point of view, which might show you a different perspective, and in this way you might find some different optimization methods that nobody even thought yet about. Basically, because the communication between CPU and GPU is just an inter-process communication, and this topic is very, very boring, I tried to do it a little bit different. So I packed it into an fantasy theme. How it will look, you will see. Okay, the agenda is as in every RPG session. Basically, first we want to gather a party, and then we are going to get a little bit more experience before we finally get into the dungeons and try to fight the boss. So here are our contestants. So we're gathering the party. The first one, the first powerful unit is the Cedric. So basically it's a CPU. He's a human wizard, and his most important skills are the low latency, because he's a quick thinker. Big catch means big brain. Complex control, that means that he can cast very complicated spells, and low throughput. He's a lame fighter, so basically he's not very well suited to fighting vertices and pixels. So we have another hero in our pack, and it's Merlok. Another powerful unit, he's a troll, he's a berserker. Now, the high latency means that he's a very slow thinker. He has a small cache, meaning small, little, tiny brain, and no control. Maybe not exactly, but really he's not well suited to very complicated tasks. On the other hand, he has high throughput. He's a tough fighter. He can crush hundreds of vertices using the one hand and millions of pixels using the other. So he's the guy we want to work with. Now, as in every team, and not only this kind of team, the most important thing in order for the team to work efficiently is the communication. Now let's see how Merlok and Cedric can communicate with each other. So basically, Cedric is a human, and he knows only human languages, like English, whether it's British English, American English, or Australian English. He can know German, French, Spanish, and he even knows Esperanto. Of course, nobody speaks Esperanto, but he does. And it's probably the most efficient language as soon as anyone speaks this language. Now let's get to Merlok. Now, Merlok is a troll, and troll speaks trollish language. Does anyone know any trollish languages? Me neither. But from my experience, I know that the trolls use different languages based on the region they come from. For example, if they come from Shire, they use different languages. If they come from Mordor, they use different language. The same happens from the northern mountains or from Gondor or Rohan. So basically, this is gets a little bit complicated, this communication process. But moreover, the trolls, depending on the family they come from, they can even have different dialect, even if they speak almost the same language. And for example, in NVIDIA case, you have the different families of GPUs, like 7000, 8000, then GTX, Tesla, and Pascal, and they really speak almost similar languages, but still different. So we have a problem, a potential communication problem. So humans don't speak trollish, and trolls don't speak human. We need something else. So as we see this from the perspective of communication, this is a simple task. When you go, for example, to Japan, and you want to speak with Japanese people, what do? You use a translator. And this is the thing that we also need to have. So this is our third contestant, Volvo, the driver. He is the translator. Now he is called the driver, and really I don't know why. The driver maybe because he drives me mad constantly, but I don't know. Now he's got two basic things. He speaks human and he speaks trollish. The dwarves can also be distinguished between thin dwarves and fat dwarves. The thin drivers can be seen on consoles because they basically translate, and this is all they do. But on PCs there are fat dwarves because they have other tasks to perform, like keeping resources or synchronizing stuff. Now you can think also that they are fat drivers because when you download an NVIDIA driver from the net and you unpack it, it's like 330 megabytes in size, so it's much bigger than even your exe file of your game. That means that there must be a lot of stuff apart from the simple translation. So we have our party ready, a CPU, driver, and the GPU, and they can now work together. Okay, so we need to gain a little bit experience before we start fighting the boss. And the next part is called Talk Less, Act More, or in other words, silence is golden. But first, a little screenshot. Now, this is a screenshot from a session of optimization session we did on Mortal Kombat 10. And basically, the long story short, we got this patient in an agonal state, on PC at least, and we were asked to make him alive again. Although the easiest thing was to let him die simply in this agony, but we were paid to resurrect him, so well, we started. This is a screenshot from a session that took about 1.5 months after we got the source code, so we did the initial optimizations, and as you can see, the higher parts is just the CPU, so basically it's the logic and it's the game thread main. In the middle, you can see 4 or 5 of the rendering threads. So we did some multi-threaded rendering already, and but down below is the DirectX. So we can see that the GPU and the CPU is quite parallelized, but there is something strange. The strange thing is the one circled in red. Basically, the CPU is not doing anything on our side, at least. The GPU is not doing anything, and there is a strange thing. When you click on it, you can see that this is the ATI driver, so basically these are a kind of troll from Mordor, and we have a problem with this because we have a stall on the driver side. By the way, this is Windows Analyzer, a very perfect tool from Microsoft, one of the very few tools from Microsoft that really work. It's bundled with Visual Studio, so please use it. Okay, so we have problem with communication and the bottleneck is the driver. What can we do? The easiest thing, remove the driver. Okay, is it really possible? Well, first of all, we would need to learn how to talk to the troll, right, to our GPU. And yeah, there are no universities, no courses, no books that can teach you that. So, of course, there are some hints, right? You can become an employee of Intel in Gdańsk and start to write this driver. So basically, you will get to know the troll. But from our perspective, what can we do? We can reverse engineer the console driver. On PC, quite hard, but it's possible to see what's going on consoles. So if any one of you works with a console like PS4, PS3, Xboxes, you can see that all the calls are, you can see the memory, what's going on and what's happening when you do the API calls, and try to guess what it's really doing and try to reverse engineer it so you can remove the whole driver. Was it ever done? So yes, I know about at least 2 examples. The one was done on the DMC, the original one made on PlayStation 2, where they simply did not use any API, any rendering API. They were filling the DMA packets on their own and sending them directly to the GPU, to the vector unit. It was cool on the one hand. On the other hand, we had to port it to Xbox 360, and this was a nightmare. So we need to create a kind of a machine that was simply analyzing all the DMA packets and translating them to the DirectX calls. On the quite a little bit modern machine, so it was Resident Evil Operation Raccoon City. They did exactly the same. The developer did exactly the same on the PlayStation 3. So it was not using any rendering API. They developed their own API, basically. They were filling the command buffer all by themselves and then pushing this to GPU. So apart from the fact that the driver was not a bottleneck anymore because they had full control over it, they could do some additional stuff like stop the processing of the render commands, do something else in between, and continue processing this if it happened to be bottleneck, or for example, the GPU needed to wait for something that was created on the CPU. Now, on the PC, it's not really possible to do, especially because we have many different GPUs and we don't want to learn a single dialect because we won't go any far with this. We wouldn't like to sell our game for only one kind of NVIDIA card or ITI or Intel card. The one thing below, the native words, it was a little bit, the thing that got me to think about reverse engineering the drivers and trying to see what they are really doing was the thing that the documentation for DirectX 9, for example, says that some things are impossible and they are not existing. But if you were using the extensions from NVIDIA or ATI, you could do some tricky stuff in order to gain the performance on the CPU side. And this means that the different GPUs are using different languages and they have different extensions. Okay, but what else? If we don't want to reverse engineer the thing, what else can we do? So basically, if the problem is the driver, we want the driver to do as less as possible. Since his main job is to translate our stuff, we want to talk as less as possible. And the way to do this is just to see what the driver is doing in between when we talk to him and try to mitigate any problems that might come up with that. And now we're going through some basic optimizations that you probably already know, but from the communication point of view, so you will see why they are really working. Okay, the first thing in order to decrease the number of talking to the GPU is the state batching. So basically we want to set all the rendering states like blending states, like rasterization states, culling states and so on just once, then make a bunch of draw calls and go on. Now in DirectX 10 Plus and newer APIs in Vulkan 2, this is by design, let's say, and you have no other options because you have to set all the rendering states in advance before doing any rendering at all. On consoles, on the other hand, when you look at it and when you see how the buffer is being filled up, you can see that every call is inline. So this is not really a big performance problem. But since the new APIs tell you do this really once and not often, there must be some point why to do this. And for example, now the very common way of rendering is to cut the rendering pipeline into passes. As I've been to other presentations along the Digital Dragons, I could see that many people are doing this and are cutting things in pass. Even the Vulkan renderer, for example, the Vulkan API, it requires you to create something that is called a rendering pass before you even start rendering. Now the funny thing is that when you do this way, the driver can do some micro optimizations. Knowing what stuff are you going to render, he can do some additional stuff in order to make these things a bit more efficient. The most important thing is the depth pass, the most visible thing. Because when you set for the depth pass the right render states, basically you remove the pixel shader completely and set the right mask to 0 so the color rights are not even enabled, then the pipeline is switched into a version where it goes with 2 times speed. So not only you get benefits of the depth pass, for example, no overdraw and minimize the pixel shader cost in the additional passes, the depth pass is 2 times fast as could be. Now what else can we batch? We can batch resources. Of course, everybody is doing this, and every engine has things like sorting objects, but materials, shaders, textures. This is of course something that is so common that nobody even thinks about it. But we can reuse it even more. Texture atlases, a common technique, right? If you're rendering a creature and you want to use 4 textures to use this creature because he has some wooden stuff and some skin stuff and some metal stuff, you can basically put in in one texture atlas, so in one texture, and skin and color this character using only one texture. So there is only one call to the API. Another addition are texture arrays. I think that it's possible to set just one big texture array containing all textures from that are being used in a frame, and simply with one API call set all the textures instantly. Of course, I've never seen it to work like that, but other examples are in Unreal Engine 4 when you are rendering the lightning. So all the light probes, the cube textures, are set into the one texture array, a very big one containing like 256 textures. and they are then accessed by the compute shader. Other things are like, for example, animation, like you're making a sprite animation. So you want to have many frames. You put each frame into the different slice of the same texture array, and then again, you set it only once. You set just one texture, and the shader has access to all of them. So we can batch resources like texture. Can we batch shaders? Of course we can. The shaders contains ifs. Old shader model 3.0 could be used that with branches. Now the current model contains a full scope of switch case, if, for loops, and stuff like that. So you can really do different things with only one shader. Why is it really important? It can be important because when you set a shader, the driver is not only pushing some stuff to the GPU, he is also patching the shader. We will talk about this a little bit later on. Now these two screenshots here are basically the way when the same shader with a branch operation did not work at all. The above one is the split second game, where just there was a one shader for coloring the sky and coloring the ground. As you can see, the sky from the ground is clearly distinguished, so it was working okay. Now in The Witcher 2, Assassins of Kings, it was not working because although there is approximately the same number of pixels of sky and approximately the same number of pixels of ground, let's say as in split second, it didn't work. The problem was really on the GPU side because branching was not triggered at all. I will tell you why again in just a minute. Okay, what else can we batch? We can batch draw calls. Now, not many people do this because it's hard to really render whole scene using a one draw call, but it can be possible. For example, in Ace Combat Assault Horizon, where we're using the instance drawing, I hope that many of you use it for rendering foliage, grass, maybe particles. In Ace Combat Assault Horizon, they did it, I think there were only instance draw calls. Basically, the scene that you can see on the right side was constructed with around 50 draw calls. So there are several draw calls for rendering the machines. Then there was one draw call for rendering the whole terrain. Then another one draw call for rendering the city, if it was visible, of course. And per each emitter, there was only one draw call. Yes, I know, it's hard to believe, and it's possible because the guys did it really in a, let's say, smart way. Basically, for the particles, they were creating in pre-processing some distribution functions. They had a distribution function for the random pattern, they had a distribution function for the sizing, for the rotation, for some other parameters used when rendering particles. And then we were drawing the whole emitter, they just set the same buffer, for example, several times, like they bounded the same buffer with positions 2 times in order to make an interpolation in the vertex shader. Then they bounded the buffer with the distribution, but with a different offset. And so each trail of particles was looking different, but they were using exactly the same data. And that's why the CPU, the part of the rendering, was really not visible in Performance Analyzer for this game because it didn't do anything. There was like 50 draw calls, that's all, and the whole thing was done on the GPU. Another part of batching. Now, deferred shading. Is it really a batching? You can really think of this as batching, as doing things the same way. So first why we are creating the G buffer. So we are putting every potential information that we can use on, and then we are creating the whole scene using just the one draw call, right? Because there is one draw call for the lightning per each light, maybe some additional post-processing, but the scene is created using 3 or 4 draw calls, of course, after the G buffer is created. So you can think of this, the deferred shading. The G buffer is kind of extension for the cache for GPU. Another thing when we are in the deferred words, deferred command lists. I know that probably most of you know that DirectX 11 deferred context is crippled, and it's not really so performant as Microsoft wanted it to be. There is even an example in the Microsoft SDK, the DirectX SDK, how to use the deferred context. And there are 2 types of this. The first one is so badly written that I even won't talk about it. The second one is much better because it's utilizing the thing that we have created, the rendering passes. And each rendering pass then can be created on a different thread using a different deferred context. So basically all passes can be rendered at the same time. I mean, on the CPU. Of course, the GPU has to do them in order, but at least we are having more time on the CPU because several threads are doing different passes. Now, if we are doing this, we have two additional things. First of all, we can manage the order of dispatch calls. What does it mean? Basically, when we are creating this on the CPU, we don't have to do this pass by pass. We don't have to first create the depth pass, then the shadow pass, then the opaque pass. It's not important. We can do it in any order we wish. So we can utilize the cores throughput and the way that they are used by, for example, additional jobs. So we can use our in-game job system for creating this stuff. Another thing is, for example, the opaque pass that does not need to use the depth pass. Perhaps, I don't know how it is set up, but if it doesn't need to do this, even the GPU can do this in different order. So if the render thread doing the opaque pass has already finished, we can dispatch this call to the GPU and then dispatch the depth pass. We don't really care, not the depth, the shadow pass, I mean. We don't really care whether these two passes will be done in this particular order on GPU. We just need to set the dependencies correct. And another thing that we can do when we have deferred command lists is preparing the dynamic buffers in advance. This could be utilized when skinning. For example, the skin matrices are put in a big texture that is then used by the depth pass or the opaque pass. Normally, when you do this, you have to map the resource, and then for each object, when you're drawing is you map it, put some data and unmap it, map it, put some data, unmap it. But since we are doing it deferred, so basically before we dispatch it even to the GPU, we can do with it what we want. We can log for the whole frame the buffer with matrices, put those matrices as they come when we process the all passes, then unlock it, and then push it to the GPU. So basically we can do it with one lock, unlock, and the driver has again less to do. Okay, so if we know the basic stuff, we can now try and do some additional to see what more advanced features the driver has to offer. So in order to do this, we have to see what the driver is doing behind the scenes. The things here, descripted here, are basically the things that, for example, the driver is doing before, because this stuff is needed for us if we want to port the game to consoles. The thin drivers on consoles do not do any of this fancy stuff. We have to do this alone. So the resource bookkeeping, the usage hints that are connected with resource bookkeeping, hiding latency like double, triple buffering, then some smart optimizations concerning the Z buffer, the shader patching that I already told you about, that we're going to talk a little bit more, and the GPU synchronization. So the bookkeeping, what it really is. You can think of it like this. We are having lots of weapons that we want to give for our Gnarlak to bash the creatures, right? And in order to do this, we are pushing this all to the driver. Yes, I know the driver has a big backpack and he can keep it all, but he wants to have some things handy. Now, first thing is to keep things handy, and in order to do this, we need the usage hints. I think this will be on the next slide. So let's now concentrate on the fragmentation. Because the resources occupy space, the driver needs to allocate space for them, and this introduces some kind of fragmentation, as in any rendering engine. So the driver needs to minimize it. And how can we do? He tries as best as he can, of course, but we can help him. For example, if all our textures will be of the same size, that means that even if one texture is evicted and another one is used because of the streaming, right, processing, stuff like that, that means that when one texture 1 is evicted and the texture 2 needs to be inside, it has exactly the same size, so no fragmentation happens. This can help not only us, but the driver to keep things efficient, and no additional memory allocations will happen and things will go smooth, no hitches, no stitches. The buffer pools. In Mortal Kombat, we, for example, removed one big dynamic buffer that was used for particles, and we created a buffer pool. This was similar that the NetherRealms really did on their console version for Xbox One and PS4. So it was something like that we have a pool of buffers 500 kilobytes in size perhaps, and if we needed to use one of them, we were just taking it from the pool, filling the stuff and pushing it to GPU. If the buffer was overspilled, we took another buffer, fill it and pushed it. Now, this might seem not important because what's the difference, right? But it happens in the optimization sessions that we did that some drivers were very happy with one big buffer, but most of them were really not, because they haven't any advanced optimizations done on their side, and they were just stalling the system. So the best way to do was to somehow omit it and create a buffer pool. Now the buffer pool, of course, there is a problem with checking whether it's being used by the GPU or not, but we'll talk about it a little bit later when we get to the synchronization. Now the usage hints. This is something simple, and this is the thing that we should always remember. Just tell this dwarf what we are going to use this object for. If it is static, if it's read-only, if it's going to be used by the CPU, he can keep it more handy in his backpack, on his belt, or on the shelf before him, right? He doesn't, because either way, he will put everything into the same place, and if we ask him constantly for changing some shader, for changing some object, some texture, he will need to first search for it, find it, give it to us, then put it back. And so give him some hint, so he can do this more efficiently. Now, as I already told you about these buffer pools, we can help him also, because on the DirectX 12 in a Vulkan, and for example on consoles, of course, you can use fences to keep track whether the buffer is actually being used on that frame or is not being used, right? Remember that the GPU is doing things asynchronously from the CPU. So even if we tell GPU do something and the GPU says okay, it means that okay, he just got the idea, but he's not yet ready with the frame. And as long as he's not ready with the frame, you shouldn't use the resources that he is using. Now the driver he knows about that and tries to prevent stuff like this by allocating more memory that you really need. But sometimes he won't do this, and if we do something very, very smart, he won't just know our intentions, and this might cripple the performance. So one of the things that we can do is if we have our own, for example, buffer pool, we can call the discard and the no override to tell him we are not going to change any stuff that is already on the GPU, so the driver knows how to reallocate the memory. Or we can use fences, for example, to tell him or to ask the driver, okay, is it used on the GPU? Yes, it is. Okay, so I'm not using it, I will take a different buffer. In the DirectX 11, there are no fences, but we can simulate it with the map with the flag no block. This is exactly the question. Map me this buffer if it's no longer used by the GPU, and if it is, then he says, sorry guy. So you can try another buffer. Now the double buffering, something that is of course known and everybody is using this, but why the double buffering? The best way to see that the driver is using the double buffering is just a simple test. Per each frame, create a texture, fill it with some data, use it on the GPU. After the end of the texture, release it. On the next frame, do the same, do the same, do the same. You will see that each time when the driver is asked for the new texture, so it will, for example, in my example, it returned me in my test. It returned me exactly 2 different pointers. So it was using the double buffering. But if I did something more elaborate with the scene, he returned 3 of them. So means that he switched into triple buffering. And we can utilize this. We can think about it that this is needed. So for example, the buffer pools. The buffer pools are so cool that we don't care whether it's double buffering, triple buffering, quadruple buffering. We can make as many buffers as is needed. Basically, if we ask, give me the buffer, the first buffer, now it's used, second buffer, now it's used, third buffer, now it's used, create a new one, and then you will have 4. In Mortal Kombat, after a few minutes of gameplay, we ended up like with 10 buffers, each one with 500 kilobytes in size, and this was enough. The good point of this is that there are no jittering in the game, because the driver has all the data that is needed. We don't ever allocate more memory than we need. Okay, let's go. The smart optimizations. What are the smart optimizations? Now, I will talk just a little briefly about this because this, the hierarchical Z and the early Z is a very big topic, and you can find tons of presentations about this on the internet. This is just an indication that driver do some smart optimizations, and that if we don't know about this, we can cripple the performance. The high Z is the most evident one because the high Z is basically creating, if you have a depth buffer, it's creating a pyramid of smaller MIPS of this depth buffer, each with the correct value for your test. So when you now draw a triangle, it checks the triangle from the up of the pyramid to the bottom and checks if any of these levels the whole triangle will be discarded, then the fragment shader will not even be fired because it means that no rendering will really happen. Now early Z is a little bit different. It's fine grade because it's checking every pixel. But we can cripple this. How? For example, the hierarchical Z will be disabled if we start to render things with a different test, with the different Z test when rendering, for example, in depth test. So if you have some fancy technique that you will draw something with the less than and then something with the greater than because it renders you some mask of an object, it will cripple the hierarchical Z, and that means that you will lose the whole efficiency, the additional efficiency that the driver tried to do. The early Z can be easily discarded and removed if you used, for example, shaders that do the discard, or the shaders that try to write to the depth, because then the driver cannot expect anything sensible. He doesn't know what you are going to do. He will disable his efficiencies, these optimizations. On the other hand, although all of them are easy to cripple, we can really redo them. In split second, the guys did something very easy because after the hierarchical Z was created and the scene was done, then they rendered some fancy stuff in order to do some masking that required them to change the Z test. This, of course, crippled the hierarchical Z. So what they did, they rendered a full screen quad afterwards with the depth set to such a distance that it failed all the Z depth test for all the pixels. This, of course, didn't render anything, but efficiently regenerated the hierarchical Z. Now, things like fast clear and Z compression are also present. Now, this is hard to cripple, so I won't talk about this, but really do try to Google this stuff and read how it works. You can, for example, think how some things could be done better. And of course, the 2x speed when the null pixels shaders are set, so this is the depth pass we already mentioned. The shader patching, something that not many people are aware of. So basically the driver, when he gets the shader and he needs to submit it to the GPU, he needs to patch it. On shader model 3.0, there was even more patching than it's currently. For example, since the shader model 3.0 was done in such a way that the GPU, that each unit of the GPU that was processing pixels had to do exactly the same. I mean, process exactly the same instructions, of course with different data, a classical approach with the SIMD. That means that the driver knew that since each unit is going to process exactly the same instructions, that means that the shader can be patched. And that means that no constant buffer is really usable on the pixel shader. And it was, for example, on the PlayStation 3. It was done on some NVIDIA cards using the shader model 3.0. I don't know exactly which ones, but the patching was done. And we have seen this when doing the Resident Evil 6 remastered, when we were doing this, the port for the PC. There were so many shaders and so many permutations of this shader, then the driver that was doing the patching, he couldn't fill it all in his cache, because the driver also has his cache for the already patched shaders in order to put them to the GPU quicker and efficiently after they are first created. And because the cache was too small, it was overspilled, and he had to write it to the disk. So when we were playing Resident Evil 6, at some moment there was just a hitch, a stall, because the driver was regenerating the shaders, which didn't make it into the cache. Now, there were two techniques to omit this problem. The first one was to first render in the off-screen thousands of triangles, each triangle 1 pixel in size, because it was enough, with a different version of the shader, with a different permutation. This allowed the driver to cache all the shaders that we were using afterwards in the game, and it was enough, but Another problem was that, of course, the cache was often overspilled, so we asked NVIDIA to create drivers that had a bigger cache, and they said, okay, and the next the next shaders with, of course, some additional routines, if they found out that this is the Resident Evil 6, they changed the cache to be twice as big, and this made the game run without any hitches. Now on current GAN consoles, and for example in the shader model 5.0, the patching does not happen because the shaders are much more elaborate. They have switch case, they have loops, and each unit can really use different instructions, and that means that they need to use the constant buffers. But the patching still exists on the side of matching the buffer, the input, with the shader. Basically, the shader expects some data in some format, and the buffer can contain this data differently swizzled in different format. Now, what is the vertex declaration in DirectX, or what is the vertex layout, I believe it's so-called, in DirectX 11? Basically, this is another shader. This is, so when you set the vertex element, and when you set the shader, driver needs to patch the shader in order to create additional instructions to read from the buffer. It means that each time that you are sending the buffer to the shader to the driver needs to patch it, and this takes time. So switching the shaders is not a good thing. Of course, the DirectX 11 has things like binding. So when you create the vertex layout, you need to bind it to the shader, and this is really the micro compilation of the code, so it can be stitched together. On the Xbox 360, for example, you had a function bind. So then, after you did the bind, you never had to use any vertex shader, any vertex input. So vertex declaration, I believe it was called. So you never had to do this because it was already compiled into the shader, and no patching happened. So this is like micro optimizations, right? It gives you 5% or 2% for the whole frame. It's maybe not much, but sooner or later you will get half a milliseconds using all those additional simple optimizations. Is half of a millisecond much? Maybe it's not, but if you are on the boundary of 60 FPS and you have a fast-paced game when you really require it to have 60 FPS, then this half of a millisecond might be it's good or it's a lame game. Now, synchronizing with the GPU. This is really a hard topic because this is something that is deep inside the driver, and we don't really care about it. We don't really want to use it. This is the same as synchronization between two threads. So how can, as I already told you, the GPU is working asynchronously. And we want sometimes to know if we finished processing some data, if we finished some command list, in order to know where we are and how to synchronize with it. So basically we can ask GPU to make a timestamp, right? And Gnarlak says, Gnarlak was here because it's everything that he can write. And we know that, okay, so he's over after some instructions, he did that, he for example, already processed 2 passes, and he can, so we don't need to keep in memory some resources because they were already used. This might be useful. This is very hard to do, and I did it only once on PS4 in order to do really some very small micro optimizations to get a stable frame rate. Other things are like flashing the cache and synchronizing the compute shaders. Also, in DirectX 12 and in Vulkan, we can turn off all synchronization stuff at all and try to see how your frame looks without it. And I can assure you that it looks like a crap because, for example, the async compute shaders are async. So when you make a you're clearing a render target, it's done on a different thread, let's say, of the GPU. And when it is finished, you never know. And then when you start drawing on that render target, it might still be being cleared by that compute shader. Now, you don't want to have this because the frame will look like a crap. And if you disable the synchronizations, it will happen. Now, is it useful information for us? Maybe not, but on the other hand, if we know that, we can make the async compute shader call for clearing, then do some completely other stuff on the GPU, and after some time, try to render to that cleared render target. Because the synchronization call, of course, will happen, but it will not impact the efficiency because all shaders were already finished. And Vulkan can have even much more of that stuff because he has fine-grained barriers. So, for example, you can ask Vertex shader to wait for the pixel shader wave to finish the stuff if it, for example, created a texture that you are now going to use on the vertex shader. I know it's some very elaborate and strange things, but maybe this will be this small percent of the frame rate that you are really striving to get. A bit of efficiency. Now, maybe when I'm talking about 60 FPS on Mortal Kombat and other action, fast-paced games, is it really important because most of our games run at 30 and everyone is happy with that? Well, remember that we are going VR now, and VR needs 90 FPS at least to not make people dizzy and not make people headache, right? So 90 FPS is now our goal, and maybe sooner or later it will be like 114 on 120 hertz, and then even a slice of a millisecond will be really important. Now, to summarize my whole speech, first of all, teamwork. Yes, remember that this is a communication process. We have a GPU, we have a CPU, they will need to work together, and there's a driver in between that's really always stalling, basically. Think parallel. Unfortunately, we need to recreate all our engines and make them parallel. The rendering can be done parallel. It's not blocked to the single thread. Everything can be done parallel. Now we can utilize the GPUs, multiple GPUs, so each one is doing a different thing using the APIs like Vulkan or DirectX 12. Sooner or later, we will need to do this. Batching, remember this, silence is golden. The less you talk, the less problematic it is, the less misunderstanding happens. Use command lists, of course, minimize driver work, as I showed you, and profile, profile, profile. Now, the Windows Analyzer is always there. There is also a very good tool like Intel Performance Analyzer that can grab frames and show you what's going on. Basically, those two show you the stalls, so you can see that one thread is waiting for another. And experiment. Of course, there is no silver bullet, yes, I believe it's called. Nothing like that, and in each of your games things might change. The cache might be different, the texture sizes might do better if you just make them a little bit bigger or a little bit smaller. Yes, bigger. Remember that there is something like alignment, so sometimes things that are bigger might work quicker than things that are smaller. And of course try the consoles, because on consoles you can see everything. On PC most things are hidden inside the driver. On consoles there is no driver. You can see everything that happens. And you can be quite sure that same things happen on the PC side, because basically who did the graphics card for the current consoles? Well, the same company that are making the graphic cards for PCs from years on, and it happened always. And I think that, at the end of this presentation there are some links. The first one is really a good comparison between what the CPU and GPU is and what is not, so the differences. Some video memory profiling example with the Windows Analyzer. The Z-buffer optimization by Patrick Kotzi is a very good presentation, but I've found many other that can talk about Z-buffer optimizations. And if someone is really interested in the synchronization, the low-level synchronization on the GPU, the Vulkan variants explained, they are not really explained so good, but at least this is a kind of start. But thank you, and if anyone has any questions.
Hey, have you heard about the tool called GPU View? Because I guess that would be much more sophisticated than this Windows Analyzer that you showed.
Yes, I heard it, but the question is whether you are really interested in what's going on the GPU or what's going on in the whole system. So I know that the Windows Analyzer is not the best one, and there are other. But for example, it's firstly, it's bundled with Visual Studio, so if you have Visual Studio, it's for free. Secondly, it shows you everything that's happening on your PC, and you are usually interested in the stalls. So basically, who is not working, because my game is working and the GPU is 99% done. So what's going on, because I still have 13 FPS. But yes, this tool is awesome, and I also seen it.
Hi, actually I have two questions, so if you can ask and answer one after another, that would be great.
Okay, go on.
The first thing, the batching many objects into one draw call comes at a price. For instance, you can have different objects requiring different data, but the data, all the data for all the objects need to be sent to the GPU within one draw call. So you need to send unnecessary data for some of the objects which you need to render in the same draw call. So that's a trade-off. Do you think this trade-off is worth it? So do you think that sending more data to the GPU so that to render only in one draw call would be okay, would be something to go for?
Yes, so the real thing is about whether you are doing the same thing or not. So if you are going to draw hundreds of buildings and they look exactly the same, then yes, do it with the instance drawing. If you're going to do it with particles, then it's cool. It also works with, for example, foliage. So basically you are drawing a huge number of the same looking objects. But if you want to do this to draw things that are different and basically they need to use a different data set, then no, because the cache, as I told you, the Gnarlak, the troll, has very small brain. He has got a very small cache. So if you want to draw hundreds of objects and each one will use a different texture or a different, even it's using, for example, the texture array, but it's using a different slice of the texture, then probably this won't fit into the cache, and the cache will spear, and then will be a cache missing, and that's really hard on it hurts GPU. So first of all, you need to experiment, and secondly, you need to know exactly what GPU is good at, right? And he's good at doing the same thing on the very small subset of data. So, or at least the data that is that has a locality. So the data that is close by. So, for example, even if he must evict something from the cache and load additional stuff, make sure that he won't need that evicted stuff later on. So, of course, in Ace Combat Assault Horizon, it worked great. In Rime, where you had a huge number of patches of grass, weeds, and some additional foliage, rocks, it didn't work really well because the, I don't know, textures were too big, the objects were too big, there were too many of them. Simply on PS4, it was quite okay. On Xbox One, it was so lame.
Okay, so batching only the objects which are quite similar.
That's true.
Okay, so then the other question that I had is no longer valid.
Okay.
You've been talking about branching shaders to avoid using different kind of shaders. Is there any cost or any significant cost of using such branches in the shader, or is it somehow pre-caged that we have, for instance, some constant buffers set up so we know exactly, the GPU knows exactly which branch will be used now, or are there cases in which there's more efficient way to use two separate shaders rather than branching?
Okay, so first of all, remember that on the CPU, all the shaders are being patched. Or at least they're trying to be patched, at least with the kind, for example, to set a proper vertex layout or something like that. But as you talked about, for example, in Witcher, when we did the branching and the data was not locally available, so it's locally available. I mean, remember that the GPU is working in the blocks. So, for example, it's taking 4x4 pixels, the block, and each pixel need to execute exactly the same instructions. Not really true on shader model 5.0, but still they need to access the same data in exactly the same way. If at least one pixel is trying to do something else, all pixels will do every possible branch in the shader. And it is this is controlled by the GPU, not by the driver. So it really it depends on the scene you're rendering. For example, in Split Second, when we had the same shader for the sky and the same shader for the ground, and we had a branch inside, and it worked okay because the pixels were locally available for the sky. They were all close together, and the ground was all close together. In the case of Witcher 2, and there were the forest, and lots of trees and lots of leaves. It wasn't like that because almost in every block on the GPU, at least one pixel had a different data. And that ruined the whole efficiency. So the branching was then not good at all, and we had to do it in 2 passes. So again, this is a thing of making a lot of example tests and checking what kind of scene you have. For example, there was a talk on the VR yesterday in the morning, and they said that they were trying to use as little shader as possible. The thing was that they didn't want to have much work, but it also made a good example for the GPU, because the GPU had exactly the same shader, and the shader was just using a different path on one GPU and different path on the second GPU based on some part. And since the branching was clearly made and there was now no option that some pixel might do something else, that this was working like a charm, although the shader was a little bit bigger.
Okay, that answers my question. So it's a matter of experimentation. And
Unfortunately.
second question, or maybe a remark. You've been talking about defenses and using the buffer stack when you're trying to avoid the some mapping and non-mapping, probably.
Yes.
You've told that it's available on DirectX, I think, 12, and Vulkan, and on DirectX 11.
Defenses are available there.
Yeah, it's totally available also on OpenGL 4.4, I think, because you can do something like unsynchronized bit on the buffer, and then you have to do the manual synchronization. So you can do totally the same thing that you've told about, just as the GPU of the buffer is
Thank
used.
you, good remark. I agree, I'm very lame on OpenGL.
As a fan of OpenGL, I had to remark it.
Cool.
Thank you. Okay,
Thanks.
that's all. Thank you for presentation.